In this video, we're going to be looking at doing a full proof using rules of inference and rules of replacement, but we are going to be starting off with natural language. And the first thing we'll have to do is do a translation. So here we have a full argument. A doctor must disconnect a dying patient from a respirator if and only if the fact that patients are self-determining implies that the doctor must follow the patient's orders. If a dying patient refuses treatment, then the doctor must disconnect the patient from a respirator and the patient will die peacefully. Patients are self-determining. Therefore, if a dying patient refuses treatment, then the doctor must follow the patient's orders. So when we're doing this, the first thing we probably want to identify are what simple statements are repeated. Now, sometimes they're going to be word for word the same. Sometimes we have to figure out which statements are saying the same thing and just make sure that they are. But let's look at this. So a doctor must disconnect a dying patient from a respirator if and only if. All right, so here we recognize a operator, if and only if, okay? Now we remember that that if and only if is symbolized with a logical equivalence, and it needs a statement on one side and another statement on another. So we can be pretty sure that this statement, a doctor must disconnect a dying patient from a respirator, that is a statement. And it makes sense to say that it's a statement because that statement is either true or false. We don't know if it is. In fact, the sentence isn't saying it's true or false. It's just saying that under a certain condition, it must be the case. So we're going to get a symbol, and let's just say D. It has doctor, dying patient. It doesn't matter what letter it is, so long as it is consistent. Doctor must disconnect a dying patient. All right, now what we want to do is we want to see if there's another statement like that. So as you read through this, look at this. Then the doctor must disconnect the patient from a respirator and, well, so look at this. This statement right here, that's the same, all right? So we can have that as a D as well. And so here's another operator, and we'll use the little dot to symbolize our and. And now I'm kind of just bouncing around here. This says if a dying patient refuses treatment. So dying patient refuses treatment. We can't use a D because we've already used a D. Let's use an R. And our if then is symbolized like this. If R is true, then D is true and P is true. Let's call that P. We know that R, conditional, D, and P, that's not a well-formed formula. It's not proper grammar for us. These have to be paired, so it doesn't matter how it's paired, it does. If we put the parentheses there, then that would say if a dying patient refuses treatment, then the doctor must disconnect the patient from a respirator, period. That's one statement, and the patient will die peacefully. But we're not saying the patient will die peacefully. We're just saying if this happens, the patient will die peacefully. So those are not the right places for the parentheses. We're going to put the parentheses here. In other words, or to make that a bit more clear, premise 2 looks like this. If R, then D and P. Okay. Premise 1, let's go back to premise 1. A doctor must disconnect a dying patient from a respirator. D. If and only if the fact that patients are self-determining implies that the doctor must follow the patient's orders. All right, so this word implies, we have not run across this before. So we're going to have to think through this. Maybe we'll have to think through it. But if this sentence, if this chunk just comes to us all together, we won't have to. So let's see. Well, except here we have patients are self-determining. So patients are self-determining. Let's do an S there. So premise 3 is simply S. Therefore, if a dying patient refuses treatment, and we had R for refusing treatment, then the doctor must follow the patient's orders, and we will use an F for follow. So this is an if R then F. So if R then F. If the fact that patients are self-determining implies. So what does the word implies mean? It seems to mean that, it does mean, that every time this is true, since it implies this must be true as well. So that fits our conditional statement. So we're going to do this. D is true if and only if S is true for patients are self-determining. Then follow, and this is our argument. Okay, so what I'm going to do, I wonder if I can erase this. I can. Okay, so we're going to, now we have this. We don't need this information anymore. The natural language stuff, now all the information we need for our language is in symbolized form. So I'm going to erase all of this for now. Make this a little bit bigger, the eraser bigger. Okay. Now, this is just a matter of solving the proof like we did before. And I'm just going to get it written over here. Premise one, D. Let's get some better handwriting here. D, if and only if, S, therefore F. 2, if R, then D and P. 3, S, therefore if R, then F. Okay, now we solve it just like we would using rules of inference and rules of replacement. All right, so we're looking for if R, then F. We have an S. All right, here's something that we know. We have a logical equivalence in 1. Now, the only rule that we have that uses equivalence is our rule called equivalence. And remember that the rule of equivalence has 2 different forms. P equals to Q. If that's true, then we can have if P then Q and if Q then P. In other words, this means both of those. We can also have both P and Q are true, and P is false, and Q is false. Okay. So what do we want here? Let's see. If we did, let's just see. If we did, I'm sorry, this should be an or here. All right. Well, I'm in this position where I'm not quite sure what to do. So, like I usually do in such situations, I'm just going to start doing anything I can. So I'm just going to start doing the first formulation. If D is true, then if S is true, then F is true. And if S then F is true, then D is true. And we gotta bracket this off. All right. Now, suddenly I'm thinking about our rule of thinking of our rule exportation, which allows you, if you have a conditional like this, where you have one conditional on the left, and then these 2 conditionals parenthesized off in the consequent, then you can do something like this. I'm not actually going to do it, but this is how exportation works. If I have if P then if Q then R, I can turn that into P and Q, therefore R, which allows me to move this S around. And look what I can do here. Once I have this in position, then I can do, not quite that, but I can do Q and P, therefore R, through commutation, and then back using exportation again to give me this. And if that's the case, then the Q would be S, because see how the Q is S there. Then I can use premise 3 and modus ponens, and we'll be making progress. So before I can do that, I have to simplify. Premise 4. So it took me a little while to kind of see things, but I think now I feel a little bit more confident. If D, then S, therefore F. That is from 4 simplification. I forgot to write. This is from 1 equivalence. 6. So now we have if D, then if S, then F. And I will use exportation to give me D and S, therefore F. This is 5 exportation. 7, I will have commutation S and D, therefore F. 6, commutation. 8, I will use exportation again. So now I have this, 7, exportation. Use modus ponens to give me if D, then F from 8 and 3, modus ponens. All right, so that's finished that track. What do we do now? All right, we're trying to get if R, then F. And premise 2 says if R is true, then D is true and P is true. And if D is true, then F is true. So if I can get line 2, so this should, I see it, but now, okay, here's something we haven't really talked about yet. This is premise 2. If R is true, then D and P are true. So whenever R is true, you know D must be true, and you know P must be true independently of each other. So of course this is true. Now the trick is how to prove it using our rules. Just because you see something obviously true, it doesn't mean you can just assert it. You need to be able to prove it, because otherwise it's just extreme confidence, and extreme confidence is not the same thing as logic. So we're going to start off, how are we going to think about this? All right, if we have a conditional and we need to break up that consequent of D and P, I don't know, let's use implication, not R or D and P from to implication. All right, now we can use distribution. So distribution allows us to do not R or D and not R or P. And that is from 10 distribution. All right, now 12, we can use simplification to just give us not R or D. That is 11 simplification. And 13, now we can use implication again to give us if R, then D. Ah, there we are. 12 implication. That's what we wanted. So now we have if D, then F on line 9. If R, then D. So if R is true, that makes D true. And if D is true, then F is true. So we use the rule hypothetical syllogism to give us this. And that is from 13.9, hypothetical syllogism. And there's our conclusion. And so that wasn't so bad. It took a little figuring out. I didn't really know what to do at a couple different points. I didn't know what to do here, and I didn't know what to do there. But I just started applying rules that I knew how to apply. Kind of had a strategy, like this one, I had a background strategy. I kind of knew where I was aiming, but I didn't know how to get there. I think same thing up here. I wasn't even sure if this is the right form of equivalence for me to use, but it turned out to work. There are probably alternative solutions for this. Maybe you even solved it in fewer steps, but this is a valid answer. Well, thank you, and see you in the next video.